Hello everyone, in this video we are going to discuss bending. Beam bending theory is based on the hypothesis that bending a straight prismatic element introduces curvature. Consider an unreformed prismatic beam as shown. As it can be seen from the transverse section, the z-axis passes through the centroid of the cross section. When a bending moment is applied at each end, it bends as shown. This causes the materials within the bottom portion of the beam to stretch and the materials within the top portion will compress. Therefore, between these two regions, there must be a neutral plane as the horizontal fibers of the materials neither shorten nor elongate. Here, rho is referred as radius of curvature. We assume that a cross-section normal to the neutral plane will remain plane and normal during bending deformation. With this assumption, we will now consider bending of a small element ABCD. As it can be seen, BD elongates to BD prime, while AC decreases to AC prime. However, AB, which is located on the neutral surface, does not change its length dx. The change in length of a fiber located at a distance of y from the neutral axis is shown as del x. For a small deformation, the corresponding angle change d theta is d theta equals dx by rho equals negative del x by y. Also, from definition of the strain, it can be written that epsilon equals negative del x by dx equals y by rho. Substituting equation 2 into equation 1, we get epsilon equals negative y by rho. For the figure on the left showing the strain distribution, this important result, epsilon equals negative y by rho, indicates that normal strain will vary linearly with distance y from the neutral axis. Here, the maximum strain occurs at the outermost fiber, with distance y equals c. From the shape shown, distribution can be written as epsilon x equals negative y by c times epsilon m. The figure on the right, showing the stress distribution, similarly, if the material behaves in linear elastic manner, so that the Hooke's law applies, the stress distribution is also linear. Therefore, like the normal strain variation, stress sigma varies from 0 at the neutral axis to the maximum sigma m located at distance c from the neutral axis. Therefore, we can write stress as sigma x equals negative y by c times sigma m. Location of neutral axis. It can be proved that for a member subjected to pure bending, the neutral axis passes through the centroid of cross-sectional area, as long as the stresses remain in the elastic range. In order to determine the maximum normal stress, sigma m, in the member, the following formula can be used. Sigma m equals m times c by I, where m equals the resultant internal moment, can be determined from the method of sections and the equation of equilibrium and should be calculated about the neutral axis of the cross section. C equals the perpendicular largest distance from the neutral axis to the point farthest away from the neutral axis. This is where the stress has its maximum absolute value. I equals moment of inertia of the cross-sectional area about neutral axis. Since sigma x equals negative y by c times sigma m, the normal stress sigma at any distance y in the member can be determined using the following formula. Sigma equals negative m times y by I. Either of the above equations is often referred to as the flexure formula. Now we are going to look at the procedure to solve the problems. Step 1. Identify the location of the neutral axis by finding the centroid of cross-sectional area. Step 2. Using the methods discussed in Lab 1, find the internal bending moment, M, at the point where the bending or normal stress is to be determined. If you are looking for the absolute maximum bending stress, then you need to draw the bending moment diagram to find the maximum moment in the member. Step 3. Calculate the moment of inertia I using your knowledge from statics. Step 4. Use either of the equation sigma equals negative m times y by I to calculate the normal stress in distance y, or use the equation sigma m equals m times c by I to find the maximum bending stress in the member. Now we will look at an example. If the intensity of the load W equals 5 kilonewtons per meter, calculate the absolute maximum compressive and tensile stress in this simply supported beam. The beam has the shown cross-sectional area. First step is to identify the location of the neutral axis, which is centroid of cross-sectional area. Based on the triangular shape of the cross-sectional area for this beam, the neutral axis is in 100 millimeter distance from the base. Second step is to draw the bending moment diagram to find the maximum moment in the member. Based on the moment diagram, the maximum internal moment in the beam is 22.5 kilonewton meter. Third step is to calculate the moment of inertia of the cross-section about the neutral axis. For triangular shapes, the moment of inertia is 1 by 36 times base times height to the power of 3, where in this problem base is 150 millimeters and height is 300 millimeters. Finally, the maximum compressive and tensile stresses occur at the top and bottom of the cross-section, respectively. The absolute maximum compressive stress is 40 megapascals, and the absolute maximum tensile stress is 20 megapascals. I hope this tutorial was helpful. Best of luck with the lab!